Okay, today we start to learn about our third major type of bonding, which is covalent bonding. We've learned about metallic bonding between metals. We've learned about ionic bonding, which is mainly between metals and nonmetals. And that leaves the bonding between nonmetals, which we call covalent bonding. At the end of this chapter, we'll have an understanding of this bonding, that they share their electrons to gain stable outer shells. It's that valence shell, that's where the valent comes from, and meaning that they're sharing. We'll know some of their properties, that unlike metallic and ionic compounds, that these generally have low melting temperatures and generally composed of small molecules, not the big lattices that we see for metals and ionic compounds. Okay. Is it going to let me advance? Yep. So, common properties, that they don't conduct electricity as a solid or a liquid, and this has got some consequences. That we know that electricity is charges moving, and from the fact that they don't tend to conduct electricity, it has to be that there's no charged particles that can move. Generally, they've got low melting and boiling temperatures, which suggests to us that there's weaker forces within these compounds, and that they don't decompose as gases, like decompose, fall apart, and that means that they've got a different structure, that discrete, meaning separate molecules, and this is not a lattice like ionic or metallic, and so that these substances will decompose as gases, they'll separate into their elements. Covalent compounds don't. So what can we conclude from all of this? That there's strong forces within the molecule, and a key word for us here, intra, within the molecule, it's strong, and that is like ionic and metallic. This 3 lines here means is equivalent to. But there's weak forces between the molecules, and so the intermolecular forces, and we're going to learn more about that in the next chapter, they're weak. So how do covalent bonds work? It's reasonably simple, that they share electrons to get 8 valence electrons. And if you share one electron with something else, we say you form a single bond. And I'm going to show here 3 different ways that we can represent this single bond. And the first is like our shell, that we've got here a hydrogen atom with its 1 proton in the middle and 1 electron, trying to bond with another hydrogen atom, and so 1 proton in the nucleus and an electron, and that they can both get a complete outer shell if they share these electrons, 1 each, and so that we've got this pair of electrons which they can share to get a complete outer shell. Another way of showing that, in a very common way, is what we call a valence structure, and this one really highlights the skeleton of a molecule, and in it a line means that there's 2 electrons, a shared pair, and that's what it says here. A single covalent bond can be indicated by a straight line, and so this is much simpler. The downside of this is you can lose sight of the fact that this is 2 electrons, but it is good for showing a structure. And the third main type is what we call a Lewis structure, and in the Lewis structure you just show the valence shell as dots, and so you can have it so that they both look the same, or you can have something like here where they've got a cross for the electron from one hydrogen, and a circle just to highlight that they're coming from the different atoms. Next, well, what if you had an atom like oxygen? Oxygen has got its element number 8. It's got 2 electrons in its inner shell, and we're only showing the valence shell here. It's got 6 in the valence shell, so it needs 2 more to complete that valence shell. And if it's combining with another oxygen atom, again with 6, that it can share these ones and it can share these ones and end up with 2 pairs, 2 shared pairs of electrons. And so that this oxygen atom has got 1, 2, 3, 4, 5, 6, 7, 8 electrons, and this oxygen atom has also got 2, 4, 6, 8. And also notice here how we draw the electrons as pairs. It just makes it easier for us to count them if we pair up our electrons than if we spread them all the way around the shell. So that's a good habit to have. Just like with the hydrogen atoms, I could show this as a valence structure, and here I've got a pair of the 2 pairs of electrons that are being shared as the lines that we use for a valence electron, and here they've combined it with a Lewis structure. They're showing these non-bonding electrons that we call lone pairs. They're showing them as dots, but you could show them as lines for a valence structure. Option 3, the Lewis structure, 1, 2, 3, 4, 5, 6. And so this one's really highlighting that this oxygen atom has got 6 electrons and this has got 6, but you can have these, because sharing one with this one and one with this, it's now got 8 electrons. Can you turn it off? Now, it's even possible to share 3 pairs of electrons, although this really only happens with carbon, nitrogen, and oxygen hardly ever. And so here we've got nitrogen, 7 protons, only 5 valence electrons, so it needs to gain 3 electrons to get up to 8. But if each atom can share 3 pairs, now this has got 2, 4, 6, 8 electrons, and this one has got 2, 4, 6, 8 electrons. I can show that as a valence structure. It's the 3 lines, 3 bonds, and here again we've got the non-bonding pair as this, the lone pair over here. Or I could show it as a Lewis structure like I did on the last slide. And so at this stage, it's worth doing some practice. Start drawing an electron dot diagram for an atom of the following. Now remember, with this, an electron dot diagram, you only need to show the valence shell. So look at tellurium, look at where it is on the periodic table, and work out how many electrons it's going to have in its valence shell, and then we have to, put them in. And same with arsenics, only the valence shell in an electron dot diagram. The next thing it's asking us to do is to see that connection between the group that an atom is in and its valence electrons and its electron dot diagram, and therefore how many lone pairs and how many bonding electrons each of these will have. and for this one, try all the way up to question 1 to 6. Okay. Now, another thing that probably not so important to us in yet, but it's worth bearing in mind, we can make bigger molecules, what we'd call a polyatomic molecule. And to do it, we have to sort of look at the elements involved and see how many electrons each need. And the ratio is going to be the lowest common multiple of each. For example, methane. Methane is a compound between carbon and hydrogen. It's CH4. And so why is it CH4? It's CH4 because carbon, which has got 4 valence electrons, needs to gain 4 electrons or to get that complete valence shell. And hydrogen only needs 1. So because carbon needs 4 and hydrogen needs 1, that 1 carbon needs 4 hydrogens. And so therefore it's CH4. And you might like to think about, well, what would happen with, I was making a compound between nitrogen and hydrogen. That's what we call ammonia. What would the formula be here? And this is worth comparing to the ionic compounds. It's in a lot of ways similar. These aren't cations and anions, but in some ways it's like this is like a 4 plus and this is a 1 minus, or probably more likely this is a 4 minus, this is a 1 plus, and you've got that same sort of combination here. I won't dwell on this one yet. We're going to talk about more of this in chapter 9. Just gonna let me... Okay, final topic here. The representations of bonding a molecule, and for the French speakers here, you might recognize that this says, this is not a pipe. And it's pretty clearly is a pipe, but the idea here, this is like a famous picture by the painter Magritte, that it's not a pipe, it's a representation of a pipe. Like you can't smoke anything in this pipe. You can't pick it up in your hand like you could a real pipe. It's a picture of a pipe, it's a representation of a pipe, and it's got all of those limitations because of it. And why am I mentioning this? Because these are all representations of water molecules, and none of them are water molecules. And so this one here, where I've got the dots, this is our electron dot diagram, or our Lewis structure. This one here is what we would call our skeletal structure, showing the bonds. This one here is the valence structure, where we're also showing the lone pairs. This one here is what we like, you know, looking like the fat undies. This is like our Lewis, our space filling model. And this one here is like, we call it a stick and ball model, because it's got this highlighting the bonds involved here. And every one of these have got their particular advantages. This is my personal summary. It's not the best,